Costanzo Bellini from the Department of Civil and Mechanical Engineering of the University of Cassino and Southern Lazio, in Italy, and I am presenting a work entitled Hybrid Structures in Titanium-Lattice FRP, Effects of Skins Material on Bending Characteristics. This presentation is the outcome of a collaboration between our research team and another team from CIRA, the Italian Center for Aerospace Research. The idea behind this research is the production of an hybrid structure able to combine the qualities of lattice metal parts with those of composite materials. The aim of the present work consists in evaluating the effect of the skin material on the bending properties of hybrid structures presenting additively manufactured metal cores and FRP skins. This work is organized in several steps. First of all, there is the definition of the case study. In particular, the cell was identified in terms of type and dimensions, together with the geometry of the specimen to be tested and the materials to be considered for this work, that were titanium and different types of fiber composites. Then, the specimens were produced according to a two-step process. In the first one, the cores were manufactured through the ABM process, that is the electron beam melting, an additive powder bed additive manufacturing process. Then, the skins were added by co-curing the prepreg layers on the cores. After, the produced specimens were tested and the obtained results were presented and discussed. The characteristics of the lattice core are very important since they influence the mechanical peculiarities of the whole structure. As concerns the cell type, the octet truss lattice was chosen. This cell is a centered face cubic cell, formed by 12 struts that in the figures are represented in gray color, with an octagon inside, highlighted in red color. After several tests aimed at evaluating the possibility of removing the unmelted powder from the lattice, the cell side was chosen equal to 6 mm, while the truss diameter to 1 mm. The produced lattice core had a section of 30 mm for 9 mm and a length of 270 mm, while the skin thickness was equal to 1 mm for all types of material considered. The titanium powder adopted in the present research activity was made of the T6Al4V alloy, that is the most used titanium alloy in the aerospace and aeronautical fields. As concerns the skins, three different types of fiber were taken into consideration: carbon, aramid, and glass fibers. All the prepreg had an epoxy resin as matrix, and a satin wave fabrics as reinforcement, except the carbon one that was plain wave. As concerns the manufacturing process of the cores, after having defined all the geometric parameters, the first step consisted in the creation of a virtual geometrical model. For this purpose, the Materialize Magic software was adopted that was able to draw a lattice structure in a specific volume. Therefore, only the dimensions of the parallelepiped representing the core and the type and strut diameter of the cell were necessary. Once the CAD model was ready, it was exported in the slicing software of the 3D printer. The machine used was the Haram A2X, while the relevant slicing software was the build assembler. Then, the machine was prepared for the manufacturing run. The powder reservoirs were filled, and the process parameters were set. After, the vacuum was drawn in the manufacturing chamber. The electron beam was calibrated and the manufacturing chamber was preheated at 700 Celsius. As the imposed temperature was reached, the specimens were built according to the typical sequence of a powder bed additive manufacturing process. At the end of the process, the chamber was cooled down and the specimens were extracted from the unmelted powder and cleaned in a suitable chamber using pressurized air and a sandblasting machine, while the final depowdering operation was carried out in an ultrasound bath. Then further steps were required to create the composite skin. For this purpose, the prepreg vacuum bag process was chosen. FRP prepreg plies were prepared and layered on the mold, together with the lattice core. The number of prepreg plies was chosen in order to obtain a thickness of about 1 mm for all the face sheets. So 5 plies were necessary for carbon skins, 4 for aramid ones, and 9 plies for glass ones. This similarity was important to perform a meaningful comparison between the different types of specimens. All the layered specimens were covered with the release film and the breather fabric. Then the mold was closed with the vacuum bag. After the vacuum was drawn, the mold was positioned in the autoclave for the curing process. The produced specimens were tested according to the ASTM C393. That is the standard for the evaluation of flexural behavior of sandwich structures. In fact, the flat specimen considered in this work can be assimilated to a sandwich structure. Indeed, the 3D printing is usually exploited for complex shaped parts, but a flat shape was chosen for this mechanical behavior analysis. The test scheme consisted in the typical 3-point bending flexure. The specimen was placed on two supports and it was loaded in the center by a loading nose. The span length was chosen equal to 216 mm, while the loading speed to 5 mm per minute. After the starting of the test, each specimen was loaded until the fracture. The data obtained from the experimental test campaign are reported in this figure, in terms of load versus displacement. In particular, a single curve was plotted for each type of specimen that was representative of the results relevant to the 5 specimens tested for each type. From the experimental data, it can be noted that the highest strength belonged to the carbon skin structure, that reached a maximum load of about 3000 Newton, while the lowest one was obtained by the aramid skin structure, with a value of less than 2100 Newton. As concerns the maximum displacement, the highest value was reached by the Haram specimen, and it was 21 mm, while the lowest value belonged to the carbon specimen, and it was 7 mm. The curves of the carbon and the glass specimens were characterized by a linear load increase, and the latter presented a sudden load drop till zero after the maximum point. The highest flexural rigidity, evaluated as the slope of the load increase section, was obtained by the carbon specimen, while the lowest by the glass one, even if the aramid specimen presented a minor slope in the second tract of the load increase. Some images of the fracture zone were taken through an optical microscope to inspect the fracture mode. As concerns the carbon specimens, the fiber failure was observed on both the upper, just below the loading nose, and the lower surfaces. In particular, the former showed a compressive fracture, while the latter a tensile one. The most interesting thing to highlight is that a skin detachment was observed on the upper surface, and the core was not damaged. As concerns the aramid specimen, also in this case the fiber failure was observed, as for the carbon one, together with the skin detachment in the upper zone. The fracture surface of the carbon laminate was sharp and clean, while for the aramid a kind of fraying of the fibers was observed. Moreover, for the aramid skin structure, a partial failure of the core was observed. These different damaging features can explain the different shape of the loading curve, characterized by a decrease of the rigidity near the maximum load. In the last specimen, the glass skin one, the total failure of both the skins and the core was observed. In fact, after the test, the specimen was split into two halves, and this explained the reason why a sudden load drop till zero was found. However, in this case, the debonding of the skins was not observed. The aim of the present work is to explore the effect of the skin material on the bending behavior of metal lattice core structures. In particular, three different types of FRP skins were considered: carbon, aramid, and glass fiber, and the core was made of titanium alloy through ABM process. The three-point bending test carried out on all the produced specimens highlighted a better flexural behavior of the carbon skin ones, that presented the highest maximum load and the maximum rigidity, while the glass skin specimen presented the worst bending performances. Considering the micrograph of the fractured specimens, different damage mechanisms were observed and can partially explain the different shapes of the load displacement curves. Thank you for your kind attention.